In this project, we set out to explore few-shot generative modeling, and in particular, its application to upsampling minority classes in classification setting. We analyzed a particular type of transfer-based few-shot model called the EWC GAN. This model is appealing because of its relative simplicity and because it requires no architecture modifications. We use a standard transfer-based approach for the EWC GAN. We begin by pre-training a GAN on a large source data set, and then fine-tuning on a few-shot data set with similar features to the pre-training data set. The EWC GAN uses elastic weight consolidation, which employs a pre-trained model's Fisher information to regularize the generator during the fine-tuning phase. The Fisher information on a particular parameter theta is defined as an expectation of the square of the derivatives of the loss function with respect to theta, and it measures how insensitive the loss is to change in theta. During fine-tuning, generator weights are constrained to stay close to their pre-trained values according to their weights Fisher's information. So weights that were important for the pre-training task are constrained to stay close to the pre-trained values, while weights that were less important are able to vary more. Intuitively, this allows a generator to remember the important features from pre-training data set during fine-tuning, thus preventing overfitting.
We identified one main challenge with this method. It's a common issue with few-shot GANs that the discriminator quickly overfits to the few-shot data set, and this method presents no way of addressing this challenge, as regularization is only applied to the generator. We propose a number of techniques that we hypothesized would help address this issue. The first is actually applying EWC to the discriminators in addition to the generator. Intuitively, if we would like the generator to maintain the diversity from the pre-trained model, the discriminator should not penalize images that do not exactly match those from the fine-tuning data set. Discriminator regularization using EWC forces the discriminator to remember the important features from the previous task, so the generator incurs less of a penalty from generating diverse images. The second technique is a set of more standard GAN hacks, which we use as a comparison with our EWC discriminator regularization. Instance noise adds a small amount of random noise to the images before feeding them into the discriminator. Label smoothing randomly flips the labels of the images with some small probability. Both instance noise and label smoothing are ways of injecting noise into the discriminator training, which has an implicit regularizing effect. For our model architecture, we chose a 4-layer DC GAN. We modeled our architecture choice after the original EWC GAN implementation, and we note that we settled on this relatively simple architecture because we were more interested in exploring EWC methods themselves than a particular type of architecture.
For our experiments, we used 2 main metrics. One is KID, which measures the dissimilarity between 2 sets of images. Lower KID indicates that the 2 sets are more similar, which implies that the model is more effectively learning the true data distribution. The other is LPIPS, which measures image diversity. Typically, a higher LPIPS indicates more diverse images and is more desirable. We performed 3 main experiments. For the first, we trained the EWC GAN on 5 100-shot datasets, 3 of which are subsets of the pre-training dataset. We pre-trained the GAN on the Celeb A dataset, which has about 200,000 images of celebrity faces. The 3 subsets we choose are bald people, people with eyeglasses, and people with bangs. And the 2 non-subsets are 100 images of cats and 100 images of Barack Obama. The latter 2 datasets serve as examples of use cases that the EWC GAN was originally proposed for. We can see from the KID scores in the table that EWC improves image quality substantially, and that the improvement from using EWC is generally larger for the Celeb A subsets than for the non-subsets. This is promising if we're interested in using this method to upsample minority classes. A qualitative inspection of the images validates these results. However, we note that while KID decreases when using EWC, LPIPS generally stays relatively consistent, indicating that the level of diversity does not improve substantially. Next, we look at the effect of varying the number of shots on model performance using the eyeglasses dataset. As we would expect, model performance degrades as number of shots decreases, but we note that the EWC GAN still performs quite well for even very small datasets, suggesting that this method may be useful even in very imbalanced class settings. Finally, we look at the effectiveness of our proposed improvements using the bald dataset. We see from the table that discriminator regularization substantially improves generated image quality and actually outperforms label smoothing and instance noise. Also, discriminator regularization using EWC achieves the highest LP-IPS score, indicating that this method helps to maintain the diversity from the pre-training dataset as hypothesized.
In summary, we have shown the viability of EWC GAN for upsampling minority classes in imbalanced classification tasks. We have motivated the use of regularizing the discriminator during fine-tuning and shown that it can be used to improve generated image quality. Finally, we note that the quality of our image is more limited by the quality of the pre-trained model than by EWC itself, and that the image would likely improve if given a more well-tuned pre-trained model.